Hello. In the previous lecture I have derived the formula for the sum of n first natural positive numbers, and I also told you that this formula will be used in derivation of many other formulas. And now I will present you such an example, and this one will also have a nice geometrical illustration. Let's start. Derivation of a formula, problem number 2. And here is its formulation. Derive the following formula for n from the set of positive natural numbers and show a geometrical illustration of this formula. So here you see that the formula is for the sum of n first odd numbers. You see 1 plus 3 plus 5 and so on and so on. And generally an odd number can be written down as a even number. It is 2 times some number, right? It will be an even number. Minus 1, then you get an odd number, right? And symbolically we can again use this sigma symbol, which tells us that we sum a number of terms. And how many terms do we sum? Well, n pieces, because we start with a k equal to 1 and we end with a k equal to n. So it will be n numbers which we will add together, but this time these numbers are formed in this way. For each k, our number will be 2k minus 1. So now I will start solving this problem to derive the formula for the sum of odd numbers, and I will at the same time explain how to understand this short notation with the sigma. So first, if I take k equal to 1, then I have to take a number 2 times 1 minus 1, and it will be 2 minus 1. It is simply 1, right? So I will mark it here maybe with this color here, and I will write here 2 times 1 minus 1. It is the first number in my sum. Then I take another color and I move to number 3, which is produced from k equal to 2. 3 is equal to 2 times 2 minus 1, right? It is 3, 4 minus 1. Then the next one will be produced with help of k equal to 3. I will get 2 times 3 minus 1. It is obviously 5. So now you see how to understand this notation, right? I put instead of k 1, then 2, then 3, and I produce these numbers, which will be our odd numbers, which are coming directly after each other. And then the last one will be, well, I don't need another color. I will simply write that it is 2n minus 1, because now I take k equal to 1 and I plug it, k equal to n, and I plug it in here instead of k, and then I get 2n minus 1. So what I can do now, I will take a color which I didn't have yet. It can be orange. And I will put together all the terms which are twice times some number. You see? And I can factor out this common factor 2, which is present in all these terms. So when I factor out 2, I will get from my, maybe back to the old colors, from my first term I will get 1, then from the second one I will get 2, from the next one I will get 3. You see what is happening, right? I have factored out 2, and then I just have these factors which are left in parentheses. And the last one is 2n, because I factored out 2, then I have just n in this parentheses. So now I am done with this part, which is doubled numbers, right? I have already taken care of them. And what I have left here is minus 1 minus 1, and so on and so on. And how many times do I have this minus 1? Well, as many times as I have terms, and I have exactly n terms. So I simply have to write here minus n, and this minus n comes from minus 1, minus 1, minus 1, n times. So I subtract 1 n times, and this means that I actually subtract n. And now you see it's time to go back to our problem number 1 from the previous lecture. Problem 1, because problem 1 tells us what is the sum of n first positive natural numbers. So I have this 2, and in parentheses I will get n times n plus 1 divided by 2, because I know that this is the sum of n first natural positive numbers. And then I still have to subtract n. So what is happening here? I see that I will have a cancellation because it is times 2 and divided by 2 is just nothing, it's just multiplication by 1. So altogether I have n times n plus 1 minus n, and now I see that I have factor n in both terms, so I can factor it out, and in my parentheses I will have n plus 1 from the first term and just minus 1 from the second term. And you see I have cancellation again here, and altogether I will end up with n times n, which is n squared. It is exactly what I promised you that it would be. By the way, if you want to, you can prove this formula with help of mathematical induction, if you are familiar with it. If not, you can watch this free course, Proofs by Induction. But okay, now we are done with this part, and I will move to my presentation where I have prepared a geometrical illustration for this formula. And also here I chose n equal to 6, well, because it is just large enough to illustrate my point and not too large. So I have to show that the sum of first n positive odd numbers is equal to 6 squared, right? So 1 plus 3 plus 5 plus 7 plus 9 plus 11 is equal to 6 squared. So I will do this in a very similar way as in the previous lecture. So I start with a unit square, which has obviously area equal to 1 square unit. Then I take 3 squares, and you see what's happening, right? I put them like this. And here 5 squares, 7, 9, and 11. And what do I get? Well, I get altogether a large square with a side length of 6 units. And it is, well, the area of this large square is equal to 6 squared, and at the same time it is equal to the sum of the areas of these objects formed by 1 unit square, 3 unit squares, and so on and so on. So this left-hand side is equal to this right-hand side. The right-hand side represents the area of this large square, and this area can be represented with help of this left-hand side as the sum of areas. In the remaining part of this lecture, I would like to tell you several words about something which you will sure meet in some more advanced math classes. And it's the concept of a sequence and of a partial sum of a sequence. So what is a sequence? Well, basically it's a list of numbers which are numbered. So we can call them generally A1, A2, A3, and so on and so on. It's a sequence. In lecture 2, in problem number 1, we had a sequence which can be defined in the following way. An is equal to n. So A1 is equal to 1, A2 is equal to 2, and so on and so on. This is an example of a sequence here. Now, in this lecture, our sequence can be defined in the following way. an is equal to 2n minus 1. And then we get a sequence of odd positive numbers, right? Starting with 1. Then in next lectures, we will have sequences defined in the following way. Here in lecture 4, we will have an is equal to n squared. So it will be 1, 4, 9, and so on and so on. All the squares of natural numbers, starting with 1. Then another sequence, another sequence. So all these are examples of sequences. And now, sometimes we would like to know if it is possible to sum all the elements in the sequence. You see, these 3 dots tell you that the sequence is infinite, that there are infinitely many elements in this sequence. And you know that if you sum up all these numbers, then you will get infinitely large sum. So there cannot be any number which can be defined as the sum of this sequence, right? Because it will just get larger and larger and larger. But sometimes, and specifically this sequence, it is possible to sum up infinitely many numbers and still get a constant as the sum. You will see this later. And in order to formalize this concept of sum of all the elements in the sequence, we introduce the concept of partial sums of a sequence. And this partial sum look like this. So the first partial sum is simply the first element of the sequence. The second partial sum is the sum of the 2 first elements. And then you can probably guess the third sum, the fourth, fifth, and so on and so on. And if it shows that these numbers which we get kind of get a stabilization on some number, then we can say that this number it can be defined as the sum of this entire sequence. And now, these 2 first sequences which you have seen in lecture 2 and lecture 3 are examples of so-called arithmetic progressions. And what is arithmetic progression? It is such a sequence in which the difference between consecutive elements is constant. So you see here the consecutive elements which come directly after each other, differ by 1, by 1, by 1, by 1, and so on. Here, you add 2, 2, 2, 2, 2. So these 2 progressions are arithmetic because the difference between consecutive elements is constant. But these ones are not. You see here, for example, you jump 3 from 1 to 4, from 4 to 9, it's 5, so it is not the same number. So this is not an arithmetic progression. And in the course Pre-Calculus 1 Basic Notions, you can learn more about arithmetic progressions. The next lecture, lecture number 4, is just a PDF which you can read, and it's actually a very, very interesting lecture, so I would really encourage you to have a look at this document. There I have derived the formula for the sum of squares of n first natural numbers. And it is actually a very elegant method of deriving formulas for the sums of squares, of cubes, of fourth exponents, and so on and so on. And all of them are based on the same method, and all of them use this formula for the sum of n first positive natural numbers. Okay, that's all for now. Thank you for watching. Bye bye.